In this video, we will look at torque, the cause of rotational motion. Here, we see someone applying a force to a door, but isn't able to get it to move. Why? Because the door is hinged. Trying to push the door by applying a force that passes through the hinges will not move the door. So the correct way to open a door is by applying a force that doesn't pass through the hinges. But even then, the location of the force matters. When you open a door, you always open it by pushing it on the side furthest from the hinges, never on the side closest to the hinges. It's always much harder to open the door on the hinge side, which is to say, the angular acceleration of the door is less when you push on the hinge side. A force that doesn't pass through the hinges is not even called a force anymore. It's called a torque. When you're trying to make an object spin, the placement of the force matters. The further the force is exerted from the center of rotation, the easier it is to spin the object. Torque has to account for both the size and location of the force. The equation for torque is as follows. R is the distance from the center of rotation to the point where the force is applied. That's called the lever arm. We can say that the torque is calculated as the size of the lever arm multiplied by the size of the force multiplied by the sine of the angle between them. Just like force, torque is a vector. The direction of torque is given by which direction it would tend to spin an object. A torque that would tend to spin an object counterclockwise is considered positive. A torque that would tend to spin an object clockwise is considered negative. As I mentioned before, physicists love shorthand. They sometimes shorten this entire equation for torque to read like this. That symbol between the R and the F is called the cross product. It's a shorthand for taking the size of two vectors and multiplying by the sine of the angle between them. In this example, we see a force of 30 newtons being applied a distance of 0.5 meters from the center of rotation. The angle between the lever arm and the force is 90 degrees. The size of the torque is therefore 0.5 meters times 30 newtons times the sine of 90 degrees. That works out to a torque of 15 newton meters. Counterclockwise is considered the positive direction, and clockwise is considered the negative direction. Since this torque is causing counterclockwise motion, we give it a value of positive 15 newton meters. If you are able to solve this puzzle, try it for the case where the angle between the force and the lever arm is 120 degrees. See if you can visualize what that torque would look like. In this image, we see two wheels that share a common axle. Each has a rope strung around it. The smaller wheel has a radius of 0.3 meters, and its rope is pulling on it with a force of 50 newtons. The larger wheel has a radius of 0.5 meters, and its rope is pulling it with a force of 40 newtons. What is the overall torque? For the smaller wheel, we can substitute the lever arm, that's the radius of the wheel, 0.3, and the force, 50 newtons. The angle between the two is 90 degrees. We get a torque of 15 newton meters. This torque would tend to rotate the small wheel clockwise, so we will call it negative 15 newton meters. For the larger wheel, the lever arm is 0.5 meters and the force is 40 newtons. Again, the angle between them is 90 degrees. This torque works out to 20 newtons and it's counterclockwise, so it's positive. The total torque is therefore 20 newton meters minus 15 newton meters, or positive 5 newton meters. In the early part of this semester, we were introduced to Newton's laws. The first two laws state unbalanced forces cause acceleration, and total force equals mass times acceleration. These laws hold equally for rotation. If unbalanced forces cause acceleration, unbalanced torques cause angular acceleration. The relationship is total torque equals I alpha, where I is the moment of inertia, the difficulty of spinning something, which we saw in the last video, and alpha is the angular acceleration. Let's apply this to determine the angular acceleration of the wheels from earlier. The moment of inertia of the system is just the sum of the moments of inertia of each wheel. Suppose the smaller wheel has a mass of 8 kilograms and the larger wheel a mass of 16 kilograms. Then the moment of inertia of the smaller wheel around its center is given by this equation. We saw the standardized moment of inertia equations for different shapes in the last video. We can work out that the moment of inertia is 0.36 kilogram meters squared for the smaller wheel and 2 kilogram meters squared for the larger wheel. Finally, we can apply Newton's second for rotation to determine the angular acceleration. We divide the torque we found earlier, 5 Newton meters, by the total moment of inertia, 2.36 kilogram meters squared, to yield the angular acceleration, 2.12 radians per second squared counterclockwise. This video introduced torque and explored Newton's second law for rotation. We went through several sophisticated puzzles.